Hi, welcome to another video short. Today's topic is all about the average rate of change. Now, most of us are familiar with the concept of motion, and specifically if somebody says we are traveling at 100 kilometers an hour, what they really mean is at that moment they are actually traveling at 100 kilometers an hour. Yet there's another type of speed or another type of velocity called average velocity or average speed. And we use that when we know two pieces of information, um, specifically maybe the distance traveled and the time it took. Now, we have to be careful because speed and velocity are actually related, but they're two different beasties. Speed is what we call a scalar. It only gives us a value. For example, we are traveling at an average speed of 100 kilometers an hour, and it just tells us that we're traveling at an average speed of 100 kilometers an hour, while the velocity will also give us a direction. We are traveling at 100 kilometers an hour due south. And so there's a difference where speed is a scalar while we say velocity is a vector because it also requires a direction. Now in this little topic to introduce the average rate of change, I'm picking an example where the speed and the velocity are typically going to have the same value. So mathematically the average speed is distance traveled over the time it took, while average velocity is the displacement over the time it took. And like I said, in this example, the distance traveled and the displacement will be the same value. So if I said that you drove from, let's say, Toronto to Waterloo, let's say a distance of 120 kilometers in 2 hours, then we would say our average speed or our average velocity and is equal to 120 kilometers divided by 2 hours, or simply 60 kilometers per hour. So that gives us a nice little introduction. So let's add some more detail to our story, because as a good student, when you're doing your journey from Toronto to Waterloo, you're going to record some information. So let's have a look at some data points. So initially, at time equals 0, you haven't gone anywhere, and at half an hour you've gone 40 kilometers, and 1 hour you've gone 60 kilometers, and an hour and a half you're at 70 kilometers, and then at 2 hours you've gone 120 kilometers. So that gives us a chart or data points for our journey. And like before, our average speed is just let's say 120 kilometers divided by 2 hours, or 60 kilometers an hour. Now I'm going to use a symbol that looks like a little triangle. This is really, this delta is the change in time, or the change in position, or the change in something. So delta t is the change in time, and let's say in this case delta s is going to be my change in position. So let's graph these data points, and it gets a nice pictorial view of our journey. And you can see that the graph has some curves in it, and it tells us bits of information which will be useful. Now, we are going to define a graph usually as a function. So I'm going to use the function s, and specifically s of t, because we're talking about time. And this is going to represent my distance traveled as a function of time. So in other words, my vertical axis is s of t, and my horizontal axis will just be t. Now, the 2 points that we're interested in is we started at time equals 0, and we ended at time equals 2 hours. And I placed those 2 points on the graph, and then change in position and change in time is just simply the appropriate axis. So the change in time is 2 hours, and the change in position is 120 kilometers, and my average speed is change in position over change in time, which is like rise over run, and that is 60 kilometers an hour. So that gives us a nice introductory pictorial view of our average speed between time equals 0 and time equals 2. Now, I don't have to pick the beginning and ending point. I can actually pick any 2 points on my trip. And my average speed or my average velocity is going to be simply the distance traveled divided by the time elapsed. So, for example, if I'm going to be talking about what t equals to half an hour and the other t is an hour and a half, I can take those 2 points and simply calculate the change in time, which is 1 hour, and then the change in position, which is 20 kilometers, and therefore my average speed, which is change in position over change in time, which is rise over run, which simply is 20 kilometers. So I got 60 minus 40 over 1.5 hours minus half an hour. You may notice that my average speed from time equals 0 and time equals 2 was 60 kilometers per hour, but between time equals half an hour and time equals 1.5 hours, it's 20 kilometers an hour. The average speed can be different, and if you look at the graphic, you notice that the graphic itself curves, and because it's curving, it tells us that we're speeding up and slowing down. So of course, our average speed between two time points can be different. Now, I'm going to apply this concept of average speed to any function that we're going to graph. And so rather than call it average speed or average velocity, we're going to call it the average rate of change. And it's going to be simply determined by dividing the change in the value of the function by the change in the variable that the function is written in. So for example, if our function is f of x, I'm going to use the x value, let's say 2 points a and b, and then my y value, which would be the f of the 2 points, that is f of a and f of b. So the formula for average rate of change is change in function over the change in the variable of that function. You may think it is delta y over delta x, or more mathematically precise, because our function is f and our 2 points are a and b, it will be f of b minus f of a over b minus a. Now there's nothing wrong with you writing f of a minus f of b over a minus b, as long as you're consistent. You've got your data points, and when you're subtracting, you make sure you follow the same order. One of the nice ways of seeing this, I'll put my graph back up here, but it's going to be more generic. And there's my 2 data points, a f of a and b f of b. Because we're taking those 2 data points and we're actually calculating the change in the x-axis or the change in the y-axis. And let me just pop those points on. Here's a, and there that'll be f of a for the first point. And my other point, let's call that b, and then of course that would be f of b. And our change in my y over my change in x represents that distance from my change in x, and then that distance from my change in y. So again, you're recognizing my average rate of change is f of b minus f of a over b minus a. And that line joining those 2 points, that line, because it goes through the 2 points, is called the secant line. So in other words, the average rate of change, which is delta y over delta x, or f of b minus f of a over b minus a, is also equal to the slope of that secant line. So it gives us a variety of techniques graphically to determine the average rate of change. Now, if you've got your function, algebra is the best choice. And if somebody gives you a graph, you can probably get a really good estimate of the slope of the secant between your 2 points. And both of them represent the average rate of change. Now, this technique to calculate the average rate of change, and I would recommend that you use this formula for the average rate of change of any functions, let's say between 2 points a and b, of using f of b minus f of a over b minus a. But I'm going to show you an alternative way of doing this. Now, it's going to seem a bit strange, but it does have a natural flow later on in another video when we really start talking about the derivative. So I'm going to still talk about my 2 points, a of f of a and b of f of b, but I'm going to treat the b point slightly different. So let's have a look. So I'm going to have my same graph, and I'm going to basically talk about a being my first point of really interest. So a of f of a is going to be my anchor point. Now, let me just graph that there for you, a and f of a. Now my other point b, rather than calling it b, all I want to know is how far b is from a. That is, if I subtract b, subtract a from b, that is b minus a, that'll give me a distance, and I'm going to call that distance h. So in other words, the location of b is really a distance h away from a. So a has the location of a, where b would have the value of a plus h. So I don't have to use any b's anymore. I'm just interested in how far the second point is from the first point. In this case, it is h. So my a has the value f of a, and my b, which is really now a plus h, it's going to have the value of f of a plus h. And likewise, my change in my y value is going to be f of a plus h minus f of a, while my change in my position is going to be a plus h minus a. Now, likewise, because I got 2 points, the slope of the line segment joining those 2 points is also my secant, so nothing changes there. It's just that my formula, the average rate of change, which I'm now writing as f of a plus h minus f of a over a plus h minus a, which I can just simplify because the a's cancel out in the denominator, just gives me f of a plus h minus f of a over h. Now this is identical to the f of b minus f of a over b minus a. It's just written in a different way. So either way will be perfectly valid. I still recommend that you use f of b minus f of a over b minus a whenever somebody asks you to calculate the average rate of change. But I wanted to introduce this concept because it will really make sense when we take up the next story, when we talk about the instantaneous rate of change, which is tied in to the derivative. Thank you for watching.